Hey there. All right, so we are going to start looking into some calculus concepts. We call it pre-calc. A lot of stuff we've done is the prerequisite stuff for calculus. And to this, we're going to start the chapter that actually hits some key topics in calculus. One of those is finding limits. So we're going to spend a few days here just on finding limits and different ways to do that. So today we're going to use tables and graphs. You're going to need your graphing calculator. It's going to be a little bit tricky to try to do this with a video because you are going to be dependent on your calculator to do it. We'll do our best here. Now, limits are kind of the basis for which some calculus is dependent on. And so even when you take calculus, you'll start off looking at limits. And they're used in two basic problems that you address in calculus. And one of those is the tangent line problem. One of those is the area problem. We are not going to have time to get into the area problem, but we're going to kind of dig into this tangent line problem that calculus uses. Now, the big thing for us is that we have to understand really what a limit is. And a limit is a quantity that can be approached. Notice that's underlined in bold in your notes packet. It's what it is approaching. Sometimes that quantity can be reached and sometimes not. We're going to look at both situations. What it actually equals, we don't really care about. We're just always looking for what it is approaching. Let's look at a little bit of a notation here. So the limit is the value that your y value approaches. As your x value approaches some given value, we call that c for some constant. If you look at it here, we can see the limit as your x is approaching some constant of your function. Remember, that's like your y value. What is the limit of the y value? And we use a capital L to represent the limit. So now the existence or non-existence of the function when x actually equals c doesn't really matter at all. I don't care. Maybe it's undefined. We're going to do a bunch where it's undefined. So I don't really care that it's undefined at c. What I'm looking at is what is my y value approaching as the x gets closer to that c, that constant. Now we will find that the easiest way to find a limit is to do it algebraically. And algebraically, you can just do substitution to find the limit. So in these situations, you can see here, we're looking for the limit as x approaches 2. And finding them algebraically will always be our first shot. We're going to try this first. As x gets closer to 2, well, if you plug 2 in for this function, you should know that this is just a linear function. And if you plug 2 in right here, you'd end up with 3 times 2. That's 6 minus 2. So the limit would be 4. Okay, let's do a little fancier one. Here, as x approaches 2, now I'm going to put 2 in. If I put 2 in up here, I get 2 squared. That's 4 minus 4. That's 0. But more concerning is that when I put 2 in the denominator, I get a 0 here too. You can't have a 0 in the denominator, so that means it's undefined at that point. So in that situation, I can't just do that substitution. I can't do this algebraically, so I have to have some other methods to evaluate that limit. All right, so we're going to use a table. And what we do is you can set up your table so that you pick x values that are getting closer and closer to the c value you're shooting for. But you need to do that from both directions. You need to get closer and closer from the left, and then also do that from the right. And you have to think about this actually coming in closer and closer towards this c value from both directions. And don't be too quick to assume you know what is happening, because I'm going to give you some weird functions and weird things are going to happen. Don't be too quick to make any assumptions on it. All right, so here's the thing is, I bet you maybe have not used your table very much. There's not very many of us teachers currently that probably use the tables a lot. So I'm kind of teach you something sort of new on your calculator. Kind of tricky to do when you're not like in class with me, but bear with me. If you need to stop it and back it up, back the video up so you can find your place on your calculator, that's fine. Let's do something real quick. Let's go ahead and clear our RAM. So I'm going to do a second plus 712. Okay, that way I know that we're looking at the same thing when we do this. All right, now what I'm going to do is I'm going to go into my y equals, and I'm going to put this equation or this function that they have given us. And this is the same one from the previous slide that I know that I can't just substitute the 2 in on. So what I'm going to do now, some of you like to enter this like in fraction mode so you can see that it looks like a fraction. That's great, but in general, you got to make sure that you ultimately have the numerator separated from the denominator. So I'm going to do an open parenthesis, x squared minus 4, close the parenthesis. That's going to be my numerator, divided by. Now open up the parenthesis and do the same thing in the denominator. I'm going to have an x minus 2, close the parenthesis. Now, normally we try to go graph this, but that's not really what we're doing here. We're looking at the table. So now that you have that function typed in, you're going to go to table setup, which is second window. And on the table setup, it tells you where do you want to start your table. And I want to always start it at whatever my C value is, what my X is approaching. It's going to default to 0, but I'm going to change that 0 to a 2. And then if I go down, it has this little triangle table. That triangle indicates the change. It's a delta. It means the change. What are we going to increment by? All right, so what I'm going to start off by is I'm going to increment by a tenth. So I'm going to put a 0.1 there. You always have to begin your table by going to this table setup, second window. Once you have those two things determined, I skip the other stuff. Then I go to second graph, which is the actual table. And it's going to start off, and right at the very top, it's a 2, and that's an error. So I'm going to go up 1. And what you're going to see here is that 1.9. And at 1.9, when x is 1.9, my y value is a 3.9. And because I incremented by tenths, what I'm going to be able to do is I'm going to be able to fill in this box here and this box here. So at 2.1, I could have a 4.1. Okay, so now what I'm going to do is I'm going to go back to table setup. And since I've moved my table, that may not say 2 anymore. So you might want to just clear that and put a 2 again. And this time I'm going to go up by 0.01. Now I'm going to go up by 100. Then do second graph to see that table again. And again, I'm going up to see at 1.99, I'm now at a 3.99. And on my table, when I see a 2.01, my y value is 4.01. Now, if you had to guess right now, what do you feel like your y value from this function is approaching as we get our x closer and closer towards this 2? Okay, I'm going to keep moving. I'm not going to tell you what I think it's going to be. So I'm going to go back to table setup. I'm going to do this one more time. I'm going to clear out what's there and put that 2 back in. And this time I'm going to increment by thousandths. So 0.001. Once you have your table setup done, you go back to your table, which is second graph. There we go. Go up 1. Okay, at 1.999, I have a 3.999. And at 2.001, I have a 4.001. All right, moment of truth. Now we have to decide, what does it look like our y value is getting closer to from both the left side and the right side? What is that value approaching? And hopefully you can look at that and say, oh, that looks like that is approaching 4. So my limit would be 4 here. Now, that one, I wasn't really trying to be sneaky. You could probably tell pretty quickly there that that's probably what it was going towards. Again, I'm going to give you fancier functions, so we always fill out the full graph so that we don't miss out on something. Sometimes what'll happen, it'll look like this, but maybe the left side is all negative numbers and the right side is all positive numbers. Well, sometimes we miss that if we're not careful. Approaching a -4 is not the same as approaching a +4. That's more problematic, something for another day, but just an emphasis to be sure to fill out your entire table. All right, now, I know I don't want this to get super long, and I know tables are kind of new for us, but let's keep moving. All right, so we start off and we try to find a limit algebraically just by doing that substitution. Best case scenario, that works. If not, we can do a table. And then the third way that we could try to do that is to find it graphically. Now, if you find it graphically, here is the graph of this function. This is probably a function you maybe have not seen. But what it's doing is it looks like it's linear, but there is a hole in the graph. And the thing is, with your calculator, it doesn't show you that hole. So let's go back to our calculator. We already have this. Again, this is the same function I've been using. Same function right here. Still approaching 2. So what I want to do now is I want to go to my window. And I want to set my window up because I already have this function in y equals. I want to set the window up to match what I've got going here. So I'm going to have an x min, looks like from -5 to 5. And it's going up by ones. Okay, now let's look at the y scale on our graph here. It looks like it goes to about a -3 or 4. So I'll do a -4. And it goes up to about an 8. So I want this just to match what you're looking at. Okay, and now let's graph it. And hopefully your screen looks pretty similar to what this is, except that on our paper here, you can see there's a hole because we've already talked about how you cannot plug 2 in right here. This function is undefined at that point. And different things cause that to be undefined. One of those is just a hole in your graph. Now we're going to get into this a little deeper later on. Today we're just kind of looking at, oh, okay, so there's a hole in the graph. If you try to trace your graph, it's not going to, I don't know, it typically jumps over the spot. I'm tracing mine right now, and then I'm just kind of scrolling here, but it jumps over when x is exactly 2. So you don't see that happen. Now, what we can do is we can do value. So if you do second trace, number 1 is value. And if you put x equals 2, enter, you can see there that it just says y equals, and then there's a blank. Well, so that means it's undefined there. Now, while I'm talking about this value option, this is another option for you to fill in your table. If you were doing your table, you could do second trace and do value, and then put in the 1.9, enter. And then you would fill out your table by hand, and you'd put in that 3.9 that it shows. What's nice about value is that you're not in and out, kind of like we were with the table. Like I can immediately just put in a 2.01. Or actually, I think our first one was a 2.1. And press enter. And now I've got the outer ones. And now I'm coming in. And so I could put in a 1.99, enter. And I'd have these numbers to fill out my table with. So either way, you can do value or you can do the table if you're going to solve these using a table. But in a graph, you can see this would have been a little bit tricky to figure out without the hole sitting there like it does in this on paper. The next thing I want you to notice here is remember that we said that the limit, we said it was 4. So as our x is getting closer to 2, so what we're doing here is we're coming in from both directions. Oops, that's not what I wanted. I was hoping to be able to do 2 things at once there, but I'm not. So I'm coming in X is equal to 2 right here. Here is 2 on my x-axis. So I'm coming in from the left following my function and coming in from the right following my function until I'm getting close to this 2 grid line. And then what I'm evaluating is, as I do come in, what is my Y value at this particular spot? And you can see that the Y value of it is at 4. That's where that limit is coming from. You're evaluating what's the Y value getting closer to as your X value gets closer to this C value. Okay, so I kind of took a lot of time on those last two. So this one I want you to try to do on your own. The first thing you're going to do is you're going to put, well, the first thing you're going to do is direct substitution. You're going to solve it algebraically. But look what happens. If you put 1 in, boom, you end up with a 0 in your denominator. That's undefined. So that means you can't solve it algebraically. So I have a table here for you. And then down here, I want you to sketch me just a graph from your calculator on what it looks like and see if you can come up with what the limit is. So just a couple hints before I turn you loose. Don't forget to put parentheses around your numerator and around your denominator as you enter it into y equals. And then to fill in the table, you can do the table feature or you can do the value feature to fill in all 6 boxes. And then eventually, right here is where we write what we think the limit is going to be. What does it look like it's approaching? Then I also want you to go and set up your, well, I don't know. You could just do a Zoom standard, get a 10 by 10 window, or maybe just graph it and see if maybe it'll work. We're approaching a 1, and give me a little sketch of what the graph looks like. All right, so what I want you to do is go ahead and pause the video now and go ahead and fill in the table and a graph on this particular example. Don't forget to press pause. All right, let's see if we agree. All right, take a look at my table. From my table, I felt like the limit was approaching 2. And then when I looked at the graph on it, it really just looked like a parabola. I didn't notice there really probably was a hole in it, and the hole happened right here where I have this green dot. I should probably make that an open dot and show you that that's what's happening there. But what I'm looking for is x gets closer to 1. So here's 1 on my x-axis. And if you look at your screen on your calculator, it probably looks like it's approaching right here at a y value of 2. Okay, let's go ahead. There's a couple examples of those. We're going to move on. Now, when we're looking for limits, the best case scenario is that we're looking at a continuous function to do that. A continuous function is one that flows nicely from left to right with no breaks in it. A parabola, a cubic, a linear, absolute value, all of those are nice continuous functions. A discontinuous function is something that does have some sort of a break in it, like the hole in the graph that we had. Or maybe it might have like an asymptote. That's another type of break or a type of discontinuous function. So just understanding how we deal with finding the limit and what that means on discontinuous functions. So first of all, this first example here, I got this graph. I've put some holes in the graph, but rather than there just be a random hole, there's actually that is displaced, and it's now a point here. So this function is actually not undefined when x is -2. It feels like it is because there's a hole in the graph, but at -2, the function actually has a value of 3. So that's different than those previous graphs that just had a hole. These actually have a spot replacing the hole. Okay, so how does that change it? Okay, this notation right here just says find f of 4. That means find the value of the function, find the y value, when your x is 4. Notice there's no limit here. This just means plug 4 into the function. So if I plug 4 into the function for x, that's right here, it is very tempting to want to come up here along the nice pretty curve, but at 4, the value of the function is right here, and that y value is a 2. So f of 4 would equal 2. Now, when you change this to a limit, this is now the limit as x approaches 4 of this function. Now, this is a typo right here. I don't know, I may have that fixed in your notes now, but that should be an x. So as x approaches 4, we're looking for the limit of f of x. We're looking for the whole function. So change that to an x right there if you don't have it. Okay, so what I'm going to do now is remember that a limit is what it's approaching. So now I'm coming in here from the left, and I'm coming in here from the right, and I'm approaching this x value of 4. If I am approaching it, I don't remember it said earlier there, it doesn't really matter what it equals at that particular time because I know it equals 2. But that's not really what it's approaching. It's approaching this whole. And the y value at that whole is actually a 7. So that's what's different about evaluating the function and evaluating the limit of that function. So the limit is what is actually approaching. And so what is actually approaching is 7, not the 2. Okay, let's look at another one of those. And notice this is one that you should be doing by yourself, but it is kind of a different notation. So I'm going to walk you through that. So this is called a piecewise function. You're using pieces of functions at different times. Sometimes you would see this like you use a piece of a line and then you use a piece of another line, or maybe a piece of a parabola with a piece of a line. This one's kind of weird because it's a line. I can see this first thing is just a linear function. So I'm going to use the linear function anytime x does not equal 3. Sometimes you'll see that with like a less than or a greater than. But in this case, I'm going to look at the function when x doesn't equal 3. And then I'm going to look at this. This is actually a horizontal line. Just simply y would equal -5. It's a horizontal line at -5. But I'm only going to use that horizontal line when x is equal to 3. So that horizontal line down here at -5 doesn't really look like a line. It's really just a dot at x equals 3. So the limit as x approaches 3. And remember when you did piecewise functions, you would kind of come over here and use this as your test of whether I should be using this function or using this function. So since 3 would fall into this category, the temptation here is to use the -5 part of that piecewise function. But the fact that we're doing a limit overrides that. We are looking at that whole approaching game. So again, we're approaching a 3, and a 3 is right here on the x-axis. So as I come in from the left and from the right towards x equaling 3, it's approaching that dot. And the y value of that dot, that open dot there, is actually 2. So even though it's tempting to say, oh, but it's actually -5, nope, I'm doing a limit. I'm looking at what it's approaching. So the limit on this is actually going to be 2, not the -5. So I kind of have a note here that says, look at the graph. The fact that f of 3 is equal to -5 is irrelevant. From the left and from the right, the function approaches 2. All right, so we have found a way, even with discontinuous functions, to find the limit. There are some scenarios where you cannot determine what the limit is based on what's going on. And there's 3 different scenarios that might happen. So let's go into y equals right now on our calculator. And I'm going to clear out what we have in there, and we're going to type this first one in. This is the absolute value of x divided by x. This is not a function we're familiar with. We haven't done that kind of thing. And that's what I told you. I'm going to give you some weird functions. So I'm going to start off and hit math, go over to the right to number, and number 1 is the absolute value function, and just type x there. Then get out of the absolute value and do divide by X. And then I'm going to hit zoom, and I'm going to just do a zoom standard. That takes me back to a 10 by 10 graph. So I'm going to hit 6. All right, let's sketch what we're looking at here. So we have this going on, and then we have a horizontal line coming in. It's just a horizontal line straight in this way, and then it jumps up and it's over here now. Now, I should have probably talked about finding this algebraically first. Remember, you always want to try algebraically. That's quick. But 0 put in this direct substitute into the denominator is going to be undefined. So this is undefined. Now, what that means is, and you can see I did mine. In fact, I might need to fix it just because it'll drive me crazy. I'm going to undo. Oh, I can't undo my draw. Dang it. Make sure that you don't overlap your line. See how my line sort of overlapped right here and it makes it look like it actually worked? Erase that off of there if you did that. I can't undo it, but it should not be hitting at 0. What happens is it's coming in from the right, and then when it hits 0, it pops up here. It is not defined here or here. And then I'm going out this direction. So now the problem with this is that if I look at what I'm approaching as X gets closer to 0, if I'm approaching from the left, my Y value is -1. But if I'm approaching from the right, my Y value is a +1. That's what I was talking about earlier with the table. If you end up having negatives on one side and positives on the other, that doesn't work. So it's not approaching the same value from both sides. So we would say, this is limits that fail to exist. So what you would write is you would write no limit, but you would always justify that with the reason. And the reason is that it is approaching different values. Now, we will talk about ways later on when we get more knowledge under our belt. We'll start talking about how we can maybe look at only one side of that, maybe look at a one-sided limit or something like that. But for now, that would be considered no limit. All right, let's go back to y equal. Clear out that. Let's do 1 divided by x squared. And let's graph that. I didn't know if you would remember this graph or not. This is one that you would have seen before. Sometimes we look at it and we call it that volcano. If this was a 1 over x graph, that you should for sure know is the thing where it comes out like this, and then you have another one down in the third quadrant. But if the x is squared, the one that's in the third quadrant actually pops up positive, and they're both up top. So this is the graph that you're looking at. Now, if you'll recall, what's happening on that graph is you have an asymptote going right here down your y-axis. And that asymptote is what's making this be discontinuous. So if you look at the approaching game here, as x approaches 0, so I'm coming in from the left, getting my x closer to 0, coming in from the right, getting x closer to 0, closer to 0, closer to 0. The problem is these will never actually hit the axis. And so as I get closer to 0, what happens is my y value is approaching infinity. And infinity is not really a number, so I can't really say that it has a limit. So what I would write here is I would say this has no limit. And the phrase that we use to show that is we say that it is unbounded. It's going off to infinity. I can't list what the limit is. So anytime you have an asymptote, your reason for saying no limit is unbounded. Now, one thing to note here is that only happens if you happen to be approaching the exact spot where the asymptote is. If this said as x approaches 3, well, then 3 would be somewhere over here, and I would come in from the left and from the right, and I would be okay. But if it's approaching where the asymptote is, then we would write no limit, and it's unbounded. Okay, last one, and no cheating. You got to do this one. It's a fun one. Okay, so you can't just trust me. You got to do it yourself. So go into y equals. Clear out that one, and we're going to type the sine of 1 over x. And we're going to hit graph. Okay, now this is going to look like, here's your graph. It looks like it's down below here, sort of dips down, comes up, and then does this kind of thing. But I don't want you to draw that. If you just drew it, you have to erase it. I'm going to erase it. Okay, because what we have to do on this is we have to zoom in on it. Just like with the table, don't make any too quick assumptions. I'm going to do a zoom to, and then I want to zoom in right there where I'm approaching. I'm approaching x to be 0, and that's where my cursor is automatically. So I just press enter to say, yeah, zoom in right there. And you can see, okay, there's a little bit more going on there than I thought. So much so that I might do this one more time. I'm going to hit zoom in, enter. What do you think? What do you think is going to happen if we did it again? I'm doing it again just for fun. Okay, there's some craziness happening here. All right, so what we thought was just this nice little wave in here is not a nice little wave. It was underneath here. It swooped down. And then what we are learning is that it is going up, down, 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 up, down. And then it's coming back out here. But it is up, down craziness going on here. And every time I zoom in closer to this 0, it's getting crazier. It's not getting better, it's getting worse. Okay, that is a no limit. And that is what we call an oscillating function. It is flip-flopping up and down, up and down, up and down. The deeper you go, the more it's happening. And so it is not approaching a single value. So that's why I have to say that there's no limit, because it's an oscillating function. Now, that is not every graph that does that. Like a sine wave might feel like it oscillates. You don't have to put this on your notes, but think about what we know a sine wave looks like. It's doing oops, this, and might feel like it's oscillating, but not really. It zooms into a particular value here at the origin. It's zooming in to 0, 0. It is not oscillating like that function was. All right, so those are the 3 that you might come across on your homework where there is no limit. Always justify it with which scenario, what reason there was. Okay, last one. It says the limit, these are called one-sided limits. And I told you after we had a little bit more info under our belt, but I'm going to go ahead and throw it in here because we're going to play a game tomorrow that you'll need to know it. So I'm going to throw it in today. It says, if you come into one of these situations where there's an asymptote, or maybe there's a really more like the jump kind of situation, like on that first scenario on the previous slide. So what you can do is look at one-sided limit and look at the limit as x approaches a particular number just from the right. This is the way that's written. X approaches 2, and then we put a plus sign here to say we're only looking at the right side. If we're coming in from the left, then we put a little minus sign. Notice that it's not a negative 2. It's still a 2, but you're approaching from the left. And then if you're only looking at one-sided limits, it doesn't really matter that they're maybe not approaching the same thing from both sides. You're only looking at the one side. I'm just skimming this. Yep, that's what I just said. Okay, now let's try this one right here. I have kind of a fun graph of a lot of pieces going on. Got some open dots. I got a closed dot there that fills in for where these open dots are. Let's look at all the different types of problems we've covered today. All right, so here it is. I'm looking at our function. I'm looking at the limit as x approaches -2 from the left. So here's -2. So if I was approaching this function, I'd be on this red function here, and I'm approaching only from the left. And as I approach -2, an x value of -2 from the left, what is our y value right here? 0. Okay, so on this one, the limit would equal 0. Let's try it again. Let's look at the limit as x approaches -2, but this time we're going to come in from the right side. So I'm not using the red function anymore. I'm really not even using the green because I want to get closer to the -2. I'm really on this blue one coming in towards -2, towards -2, coming just from the right side, till I get right here. And the y value right here is -2. So that limit would be -2. Okay, let's try this one. Let's find the limit as x approaches -2. Now, this one is not a one-sided limit. This is saying, hey, you're coming in from both sides. You're coming in from the left. You're coming in from the right. Unfortunately, you are approaching different values as you come in from the left and from the right, and that is not allowed. So this would be the scenario where we would say no limit. And our justification is that it is approaching different values. All right, last one. Notice that this one is not a limit. It just says f of -2. That means you're just plugging -2 into the function. Now, I didn't give you the function. I just give you the graph of the function. So you use the graph to determine that when x is equal to -2, right here, it does not equal 0 because there's a hole. It does not equal -2 because there's a hole. What it equals is this spot right here, this random dot that they're filling in at that value. So when x is -2, the y is actually -1. All right, there we go. So hopefully that's making sense in your head. This is day 1 of limits. We will spend another day on it. You should have your day 1 limits worksheet. That's your homework, front and back of that. Shouldn't take too long. And I guess I'll see you tomorrow. Bye.